Now, when you picture the ultimate futuristic robot,
Oh,
right?
yeah.
Like the kind that's designed to take a ballistic hit, smash through a concrete wall, and just, keep walking.
Right, right.
You probably imagine it running on some sort of uh, glowing, magical sci-fi energy core, something straight out of a comic book.
Yeah, like a pulsing blue light in the chest that somehow completely violates the laws of physics.
Exactly.
Like it generates zero heat and just never runs out of juice. It's an incredibly persistent trope in pop culture.
Totally. But what if the secret to building an indestructible machine isn't magic? What if it's actually about combining cutting-edge artificial intelligence with a power technology that was invented, well, over 100 years ago?
Which sounds completely counterintuitive.
Right. But we've got our hands on a highly classified internal engineering document today. For this deep dive, we're looking at a text from June 2026, straight out of the Blackwire Rebels, or BWR, their R&D division.
Yeah, specifically, this is the blueprint for the BWR Fembot Apex power system, version 1.0.
Authored by lead architect MC Ronnie Dangerous.
Right, and the core design challenge they lay out here is just, I mean, it's staggering. They are trying to build a bipedal robot, the Fembot Apex, that can absorb massive ballistic impacts, survive high-mass collision forces, and, still maintain a continuous operational window of 16 to 24 hours.
Which, if you know anything about robotics, is just a massive engineering headache.
Oh, absolutely.
Because no single-source power system in the world can reliably meet those conflicting demands without, compromising somewhere.
You usually get speed or armor, not both.
Exactly. But before we even get to the tech, we really have to talk about the philosophy driving this machine. Because the blueprint opens with this thing called the Blackwire Rebel Immersion Oath.
And what's fascinating here is how that oath actually dictates the the physics of the machine itself.
Yeah, the literal engineering.
Right. The document states that the fembot is designed to be, quote, a guardian, not a weapon, a co-creator, not a conqueror.
Which sounds like PR, but it's not.
Not at all. It isn't just corporate spin. It is the absolute foundational engineering constraint. I mean, if you're building a weapon, you implicitly accept that it might blow up, right?
Sure, yeah.
You design it for maximum output, and if it critically fails, well, that's acceptable collateral damage.
Right, because it's a weapon.
Exactly. But if you are building an indestructible guardian, your power system simply cannot be a vulnerability.
Okay, let's unpack this.
Yeah.
Because this totally blew my mind. If the fembot needs to be this indestructible protector, standard battery systems just aren't going to cut it. So the designers created what they call a three-tier synergistic stack.
The 3 tiers, yeah.
And putting the primary power source, Tier 1, into a futuristic bipedal AI-driven robot is, honestly, it's like putting a steam engine inside a spaceship.
It really is.
The Tier 1 core of the fembot Apex relies on Thomas Edison's nickel-iron chemistry, which was invented in 1901.
Over a century ago. And yet, for what they are trying to achieve, it is literally the only logical choice.
Wait, really? The only choice?
Yeah, think about standard combat robots or even, the smartphone in your pocket right now. They generally use lithium-ion battery packs,
Right.
but lithium batteries rely on liquid electrolytes and very, very thin internal separators. If a chassis takes a heavy ballistic hit or like a crush load, those separators puncture.
And then the positive and negative sides touch.
Exactly, causing an internal short circuit.
And that leads to explosive thermal runaway. Like the battery literally generates its own oxygen as it burns, turning the robot into a literal bomb.
Which completely violates the Guardian, not a weapon oath we just talked about.
Oh, wow. Yeah.
Edison cells, on the other hand, use an alkaline electrolyte, specifically potassium hydroxide, and these incredibly robust, heavy iron and nickel plates.
They're solid.
Mechanically solid. They don't have those fragile, flammable components. They are physically indestructible by design. The lead architect even describes them as the power equivalent of the fembot's armor.
That's crazy.
Yeah, even if you shoot an Edison battery with a rifle, it might leak some harmless liquid, but it will never catch fire.
And the specs on this century-old tech are just ridiculous.
Yeah.
I mean, they are targeting a pack size of 40 to 80 kilowatt hours routed into a central 48-volt main bus.
Which is huge.
Yeah, to put that in perspective for you listening, 80 kilowatt hours is roughly the battery size of a Tesla Model 3. But packed into the torso and lower chassis of a walking robot.
Bipedal. Yeah.
And the durability is off the charts. We're talking a cycle life of over 10,000 cycles. a total lifespan of 20 to 30 plus years. Plus, they operate in extreme temperatures, like from negative 40 degrees to positive 70 degrees Celsius.
And crucially, they are totally immune to deep discharge destruction.
Oh, right.
You've probably noticed, if you leave a laptop or a car battery completely dead for months, the chemistry degrades and it just won't hold a charge anymore.
Yeah, it's just a brick at that point.
Exactly. But you can drain a nickel iron or knife battery down to absolute zero, leave it there for a decade, fill it back up, and it works perfectly.
Wait, okay. If they are so perfect, why aren't we all driving around in Edison-powered electric cars? I mean,
Yeah.
there has to be a catch, right?
Oh, there is a catch.
The document mentions they have an incredibly low energy density, something like only 30 to 50 watt-hours per kilogram.
Yeah, that low energy density means a massive weight penalty. You need a lot of physical mass, just a lot of heavy metal to hold that 40 to 80 kilowatt hours.
Which is terrible for a robot that needs to walk.
Right. Now, the document notes that Fembot's chassis design specifically mitigates this weight by integrating the battery housing directly into the structural frame itself, but that leads to the second, and honestly more critical flaw.
The speed.
Yes. Nickel-iron batteries have a very slow discharge rate. They simply cannot push a massive amount of current quickly.
So if the Edison core makes the robot too slow to survive a firefight, they had to find a way to cheat the physics of speed, basically, without compromising the core.
Oh.
Because what happens when the fembot needs to, suddenly sprint at 20 miles per hour or fire its hydraulic systems to catch a falling steel beam? The system demands energy faster than 1901 chemistry can cleanly deliver.
And that physical limitation necessitates the second tier of the architecture, the burst layer.
Right, so let's talk about tier 2, the lithium secondary banks. Because the Edison core is so slow, fembot uses lithium packs as a capacitive buffer.
A buffer.
And for anyone wondering what a capacitive buffer is, think of it like a giant water tank. The Edison battery is a tiny garden hose filling that tank. It's slow, it's steady, and it's totally safe.
Right.
But when the robot needs to sprint, it's like a trapdoor opens at the bottom of the water tank, dumping a massive, violent flood of energy all at once.
That's a perfect analogy. The engineering breaks this down into two specific lithium chemistries, actually, to balance the required performance with their strict safety mandates.
Okay, two different ones.
Yeah. The primary buffer uses LiFePO4, which is lithium iron phosphate.
Yeah.
It's an incredibly stable, modern lithium chemistry that provides a 30 to 75 kilowatt burst capability for standard heavy lifting and sudden movements.
Okay, so that's for the heavy lifting.
Right. But for pure, unadulterated speed, Fembot uses NMC, nickel manganese cobalt.
The sprint packs,
Exactly.
which are located down on the lower legs and hips, right next to the locomotion actuators. And those are capable of a massive 50 to 100 kilowatt burst just for running.
It's an incredible amount of power.
But hold on, if you are pulling 100 kilowatts out of a battery module the size of a backpack, that thing is going to generate an insane amount of heat.
Oh, a huge amount.
Didn't we just establish that lithium was too dangerous for a combat chassis? Fembot is literally strapping the explosive stuff to its legs.
Well, that highlights the constant balancing act in extreme engineering. The text explicitly states that NMC carries a moderate thermal risk. So to stop Fembot's legs from basically catching fire during a sprint, they implement aggressive risk management.
Like,
The sprint pack modules require integrated liquid cooling channels, or phase change thermal pads.
wait, phase change pads, what is that?
Yeah, so instead of just using fans to blow hot air around, these pads contain specialized materials that absorb heat by physically changing their state.
Oh, like melting.
Exactly. Usually melting from a solid to a liquid, kind of like ice absorbing heat as it melts into water. It sucks the thermal energy away from the battery cells rapidly, preventing them from hitting a critical temperature.
That is so smart.
Yeah, the engineers accept this localized risk down in the limbs to achieve the necessary speed, while keeping the torso, the Edison core, completely inert and safe.
There's also a brilliant tactical detail here, the hot swap capability.
Oh, I love this part.
The document outlines that these secondary lithium packs are designed using mil-spec Anderson SP350 connectors. What that means in the field is that a support unit can walk up, pull a lever, and swap out these 15-kilogram lithium modules in under 90 seconds.
Less than a minute and a half. And because the blueprint utilizes an isolated rail design, they don't even have to shut the Fembot down to swap the batteries.
Seriously?
Yeah, it's like having two separate electrical panels in a house. You can shut off the breaker for the garage to fix a plug, while the kitchen fridge just keeps running flawlessly.
The architect uses a great metaphor in the text to justify this whole setup. They compare fembot to an aircraft. Quote, fuel tanks swap, engines do not.
Yeah, that's exactly it.
The indestructible Edison core is the engine. It stays untouched. The lithium modules, those are just the fuel tanks.
If we connect this to the bigger picture, you can see how this layered approach solves the unsolvable problem. You get the invulnerability of 1901 chemistry combined with the high-performance sprint speed of modern lithium.
It's the best of both worlds.
Right. But of course, hot swapping assumes fembot has a support unit nearby with fresh batteries.
Exactly. What happens if fembot gets trapped behind enemy lines or deployed in a remote wilderness for days? To survive completely isolated without backup, fembot relies on Tier 3, the triple path synergy harvest.
And this is where the machine stops being just a battery-operated device and becomes an active participant in its environment, scavenging every stray drop of energy.
Here's where it gets really interesting. The document outlines 3 ways fembot harvests energy. Number 1, solar skin. Fembot has perovskite thin film panels integrated directly into its armor panels, like the shoulder's torso dorsal surface.
Right.
And for those listening who aren't deep into solar tech, perovskite isn't like the rigid, fragile glass panels on your roof. It's a crystalline structure that can be layered into flexible, highly durable materials. It yields about 600 to 1200 watts at its peak.
Which is basically a steady trickle charge from the sun just for standing outside.
Right. Then number 2, regenerative braking. Fembot's high-torque leg servos actually act as generators.
Yeah, that's super clever.
I guess that makes sense physically, right? I mean, an electric motor uses electricity to spin a magnet and create motion. So if you force the motor to spin backward by walking downhill or violently decelerating from a sprint, it pushes electrons the other way.
It becomes a generator.
Exactly. It captures that physical momentum and converts it back into 2 to 5 kilowatts of power.
It's the exact same principle used in modern electric cars to recharge the battery when you take your foot off the gas, but applied here to the vastly more complex kinetics of bipedal running and balancing.
Just way more complicated. And then number 3, thermal harvest. Using thermoelectric generators, or TEGs.
The tags, right.
These are placed on the motor housings and heat sinks. They literally take fembot's own waste heat, the heat generated by its electronics and movement, and convert it back into low-voltage DC power.
Yeah, tags utilize something called the Seebeck effect. When you have a massive temperature difference, like a searing hot motor on one side of a plate and cool ambient air on the other side, that temperature differential actually forces electrons to flow across the material.
Creating a current.
Exactly, creating an electric current. It's an incredible closed-loop efficiency model. Every watt generated through motion or scavenged from waste heat extends fembot's operational window. A standard active patrol goes from a 16-hour limit up to 28 hours just because of this synergy harvest.
That's a massive jump. And it enables something the blueprint calls survival mode.
Oh, this is fascinating.
Yeah, if the main batteries completely die, the solar skin and thermal harvest provide just enough power to keep fembot's sensors and AI alive indefinitely. The robot might not be able to walk, but it can watch, listen, and think purely off the ambient energy of its environment.
Think about the sheer chaos of the electrical grid we just described.
It's a lot.
You have 3 different power sources, the Edison primaries, lithium secondaries, and the triple path synergy harvest. They're all dumping power into the system while simultaneously routing power to locomotion, sensors, armor hardening, hydraulics, and thermal management.
It sounds like a total nightmare. I mean, how does the robot manage this massive cross-flow of voltage without instantly frying its own circuits?
Well, that brings us to the nervous system of the architecture, the battery management system, or BMS, and the power router.
Okay.
The precision required here is just staggering. Because the system is dealing with such high voltages from the sprint packs, if it detects a fault, like a damaged wire or an overheating cell, the system has to execute an automated disconnect in under 5 milliseconds to prevent a cascade failure.
Under 5 milliseconds. That's faster than the blink of an eye.
Literally. But the truly defining feature of the intelligence layer is the priority routing logic. Fembot operates on a ruthless hierarchy of needs.
So what does this all mean? It means fembot will literally freeze its own legs to keep its brain alive.
That is an incredibly accurate way to synthesize the logic, honestly.
Well, the blueprint lays out 5 priorities. Priority 1 is the neural and cognitive systems. Priority 2 is the sensors and comms array. The document explicitly states these 2 are, quote, never shed. They are the absolute core of the fembot's identity as an observing guardian.
Right. And then priority 3 is armor hardening. Priority 4 is standard locomotion, just basic walking. And priority 5, the first thing to be sacrificed if power is low, is burst sprinting.
So if fembot is in a 120-hour survival mode with its Edison core drained, it ruthlessly sacrifices movement. It sacrifices its armor systems. It will stand completely paralyzed in a forest using the tiny 0.5 to 1.5 kilowatt trickle from its solar skin solely to keep its AI consciousness and sensors awake. It prioritizes the mind over the body.
Which perfectly aligns with the emergent oath we discussed at the top of the show.
Oh, right, the Guardian thing.
Yeah, a weapon needs to move and strike. A guardian needs to observe and protect. By hard-coding the BMS to prioritize cognition and sensors over locomotion, the power routing logic fundamentally enforces the ethical mandate of the machine at an electronic level.
Wow. Now, with all these sci-fi sounding specs, the 5-millisecond disconnects, the perovskite solar armor, the indestructible 1901 battery core, it is really easy to get lost in the fantasy of it all.
Oh, for sure.
It sounds like a movie pitch. But there is a section at the very end of this document that aggressively grounds everything in reality.
The BWR intellectual honesty section.
Yes, the lead architect adheres to a strict rule: no confident misinformation. They explicitly separate fact from fiction, categorizing every single claim made in the blueprint.
It's a really refreshing level of transparency for an R&D document, which honestly are usually full of exaggerated promises just to secure funding.
Totally. So Edison batteries, the LiFePO4 burst tech, and the regenerative braking are all labeled proven. They are mature technologies with commercial track records. The thermoelectric thermal harvest is labeled promising, noting that yield projections might run 30 to 50% high in the real world compared to lab conditions.
Which is a very fair disclaimer.
Right. And then they draw a hard line at the integration, the solar skin armor, and the actual full bipedal integration of this three-tier system. Those are labeled design targets. The document openly admits no system of this specification currently exists.
I love the brutal honesty here. There's a specific correction in the text that stood out to me.
Oh, the speed one.
Yeah. At some point, someone evidently wanted fembot to have a 50-mile-per-hour bipedal sprint.
Like a cheetah.
Exactly. But the architect literally crosses out 50 mile per hour and labels it speculative, correcting the realistic target down to 20 to 28 miles per hour.
That's such a great detail.
And that correction is so important. It proves this blueprint isn't just a fantasy wish list drawn up by someone who doesn't understand the physics of heavy metal batteries and heat dissipation. By capping the speed at 28 miles per hour, they are relying on credible scaling models of existing technology. It represents a realistic engineering trajectory.
It's an ambitious roadmap, but a mathematically sound one. And as we wrap up this deep dive into the fembot apex, I think there is a profound takeaway here for you listening right now. Whether you're managing a complex business project, trying to optimize your own daily energy levels, or just preparing for the future of technology, there is a powerful lesson in how fembot handles its resources.
It's a masterclass in redundancy and intelligent buffering.
Fembot doesn't rely on one magic bullet. It knows its core is indestructible but slow, so it builds a fast buffer to handle the surprises. It constantly harvests from its environment, never letting waste heat or momentum go unused.
Right.
And above all, it has strict priority management. When energy is low, it knows exactly what to shut down and what it must protect at all costs.
This raises an important question, though, when we look at the ultimate goal of this machine.
Yeah.
We've seen how the Guardian, not a weapon philosophy, dictates the physical design, choosing heavy, safe, indestructible core components over light, explosive, highly lethal ones. But if we actually achieve this, if an AI robot is engineered from the atomic level up to be an indestructible observer rather than a disposable, highly explosive weapon, how might that fundamentally change the way we view the future of human-AI collaboration?
Oh, wow.
If our machines are built inherently to survive, observe, and protect rather than just to destroy, does that change the very nature of human conflict?
Wow. Think about that for a second. If the machines on the front line refuse to explode and refuse to die, the whole math of conflict changes entirely. It's an incredible thought to leave on. Thank you so much for joining us on this deep dive. The next time you picture a futuristic robot taking a hit, maybe you won't see a magical glowing blue core anymore.
Nope.
Maybe you'll see a 1901 steam-era battery wrapped in solar armor, intelligently deciding to freeze its own legs just to keep watching over us. Keep questioning the systems around you, and we'll see you next time.